So not just where they're collecting, but how do you do the back propagation of that information so that at any one location where I'm at now and where I'm about to go, I can actually synthesize what the spectrum would look like where I'm going, not just where I'm at. So that's a start. So the radio map program, if you look at sort of a complex social scene, right, as shown here, you start to fill in a little bit of that context. Who's around me and where? So that's step one. But that's not enough. We actually have a program on labeling as well. So what are those things? And so right now with spectrum in licensed bands, it's relatively easy. If there's energy somewhere, you can pretty much project what that probably is. And we use a lot of energy feature extraction in our dynamic radios. Once you start overlapping signals, it becomes substantially harder. So we're doing things like cyclostationary feature extraction, advanced statistical processing so that we can actually pull out information that even when there's overlapping, so these are large-scale interferers on top of this relatively low signal power spectral density here, we can pull out, that this is GSM, this is LTE, this is WCDMA. So that gives me from mapping where are radiators around me, what are those radiators doing? So that's akin to starting to fill in what are the conversations that are going on around me in real time. And then last but not least, the spectrum challenge and other work that we're doing, we call understanding intent. How do you actually walk up to a system, use this type of information so that we can start interoperating where I don't actually have to get in the way. Right? So if I know what you are, right, GSM, LTE, WCDMA, I can actually also start looking at the intent and the stress, right, that I may be imposing on you. Right? So typically we have policymakers that say stay out of each other's way, right? We actually believe that that is potentially, it's definitely inefficient, but problematic because that information is what allows me to know whether we can actually coexist. Right? It's not that you and I, right, in the audio spectrum, right, I speak in E and you speak in A, right? We have the ability to understand the broader level of context, right? So, we think the spectrum is full. The spectrum is definitely not full. The audio spectrum is full, right? If somehow we survive. So building in that understanding of intent, going from mapping to labeling, right, to how do I actually interoperate, where we're actually not just jumping out of each other's way, we're actually on top of each other, but still interoperating. And that allows us to fill in the complex context required so that we think there's a very different future ahead of us. We've gone through this era of broadcast, we've gone through this era of isolation, right? We've done amazing things. 4.4 exabytes per month of data, right, have, are now traveling through our airwaves every month. That's amazing, right? So we should be very proud of what we have been able to do as sort of the RF and wireless community. But we don't think that scales down the road, right? This is an exponential curve. It's like where's the demand going to come from? It does not seem like it's slowing down, and connectivity is sort of the basis of our society today, right? We expect to be connected into and around the globe. So we've got a shift, we believe, that's from the era of isolation to this era of learning. And that we think there's a huge shift in terms of how the policymakers approach this and how we actually look at the power of our machines to figure out how to interoperate. So tomorrow at the larger conference, what we're going to do is announce a major initiative at DARPA. This is one of our largest, at least my office, pushes to be able to demonstrate what this is going to look like. We're going to have our next grand challenge. You may remember I showed you the DARPA Robotics Challenge. We had the DARPA Self-Driving Car Challenge, right? We don't solve these problems, but we challenge the communities to start looking at the world differently and showing what that alternative might look like. So Paul Tillman is here in the back, and he's going to give the details of what that looks like right after the keynote tomorrow. And so we're very excited about trying to challenge the world to figure out what that era of learning is going to look like. So with that, I'll take questions if there's any extra time.
So the RF FPGA that you showed, was that a monolithic chip? You're covering 800 megahertz and 40 gigahertz.
Yep.
Is that silicon?
Yep.
Gallium arsenide?
So this is actually silicon germanium. This example, we have a CMOS version as well. So USC is developing the CMOS version. This is actually PE systems, and that is a silicon germanium chip. Now, We have another version, which actually we invented RF switches for, to have even more switching capability with less penalty in terms of there's always going to be adaptability versus performance trade space, right? Just like an FPGA is not as good as an ASIC, an RF FPGA won't be as good as a hand-built system. So there's a variety. There's CMOS, SIGI, and then SIGI with an upgraded phase change RF switches, which are, we can get into the details of the materials there, but it's GST is the material that actually allows you to melt and recrystallize into either conductive or non-conductive form. And that has a 2 order magnitude higher figure of merit than a typical solid-state switch.
You didn't mention anything about the power output, but with so many PAs on there, is there a thermal challenge with that?
There is. So actually, this chip still would have a power amplifier. This is sort of everything up to the power amplifier. The power amplifier, we have wideband and sort of arbitrary waveform amplifiers we've also designed. We're not doing that on chip. Thermal being one of the reasons why we do not do that. This is really the signal generation, the down conversion block, everything from the PA back the LNA, the mixer, and the like. So that is, this exact version is monolithic in silicon germanium, but we have about 10 contractors working on that. So there's a variety of different solutions emerging. But the most mature, because it's using a very stable manufacturing process like silicon germanium, is the BA. Yeah?
There's no question that the silicon and semiconductor portion has gone leaps and bounds to digital signal processing. There's a very unsexy component of wireless which is called an antenna.
Yeah.
I know that there was the reconfigurable antenna program and so on to try and build wideband antenna.
Yeah.
Where are you regarding trying to map this amazing power to the real world outside, which is this RF board?
Yeah, so we do have a reconfigurable antenna program. It is going from L-band to X-band. We also have wideband antenna. It's under development. So there's kind of an active fight, right, in terms of does the antenna world look like one or a couple of really wideband antennas, or do you actually need to reprogram that antenna? My answer was to reprogram the antenna. I actually created the program, which was sort of recap part 2. But I think that's still an open research question on, because what's happened in the meantime is that there's ultra-wideband antenna capabilities that have emerged. Now that's obviously form factor limited, right? So that's the
You
challenge.
always have a limit of how low you can go.
Yep.
And that's where things get really big and annoying.
That is true. So because this chip goes from basically, it actually goes 20 megahertz to 20 gigahertz, doesn't mean you'll instantaneously, pair an antenna that capitalizes on all of its capabilities. So the PA and the antenna are the two, so it would be the personality for the instantiation of that. We make wideband PAs, we make configurable PAs, we also make configurable antennas. Even before that, right, this is still a useful capability for, maybe 800 megahertz to 6 gig is an example where you can get wideband antennas. Go ahead.
So did you say that an IQ mod and D mod is involved in it?
Yeah. So the IQ mod, so a couple of local oscillators, so independent local oscillators that allows me to, I can have 4 channels, so this exact example would be 6 channels, so I can put it in MIMO configuration. So these are all full down converters. I can actually have more isolation if I start routing this around, so let's say I go through 4 for 1 channel. So those are the trade spaces that I get to play as a user. So the code base allows me to select, how many different, down converted blocks am I going through, where I get more and more isolation and more spectral isolation as you go through. But individually, they're IQ demodulators. You can go from a superhet to a heterodyne and make those choices. And that's part of the 2 to the 250th states, right? Is that you start playing with these large-scale architecture choices, and then within each of those architecture choices, you start tweaking the parameters of the power versus linearity versus noise figure in the LNA as an example.
What are those stages, which are the noise figures you can have?
Yeah, so there are many different teams, so just focusing on this one. In SIGI, actually the noise figure is reasonably good. It depends on the power. Right? So you go from around 2 dB to 10 dB, depending on how much power you want to throw. But that's actually, I think, one of the benefits of these type of solutions, we practice worst case scenario engineering in RF almost all the time, right? If you think of a spectral mask, you think of a spec sheet, right? It's like, what do I need in the worst case scenario? My noise figure is 2 dB because I'm at the edge of my cell and I'm sensitivity bound and I have to have that capability. So I usually burn too much power, and when I could actually have been 10 dB just fine when I was closer to the system. So I can actually start getting rid of this worst case scenario tyranny that is baked into all the specs inside of our RF design. So 2 to 10, right? So we think of it as a bubble of capabilities, right? Where you have 2 dB, sort of the best you could possibly do, right? You could always put another amplifier below that if you wanted to, but 2 dB inside this chip, and then pull it down to 10 dB or whatever you want gracefully between that, and you have power versus linearity trades. If you think of my spec sheet for an LNA, right, I got 2 dB for a noise figure, and I have linearity as a spec. Right? That means I'm at the edge of my cell, and I happen to be next to the very large other transmitter. That rarely happens, right? I think my bandpass filter, I have a bandpass filter that's this wide, right, with the fear that I'm going to have a transmitter here and a transmitter here and I'm goal posted. That never happens, right? Actually, you try to find that happening where you're actually going to saturate your RF radio simultaneously on both sides of your system, yet that defines the bandwidth of our pre-select filters, which defines the noise figure, which defines. So that tyranny of worst case scenario, right, is what we're trying to get rid of here. Each of these has filtering blocks inside of it that are tunable from around 100 megahertz to 2 gigahertz, sort of open, wide open, receive all signals, or protect ourselves when you actually need that.
So that includes the free filters?
It has an impact filtering bank, so it has some levels of filtering for an on-chip solution. Whether that's good enough for an installation next to a really, on many military systems, you probably have to still do a specific pre-select filter. We have tunable pre-select filters that pair with it, but it is relatively robust especially from a consumer perspective. So you're always going to be able to find very large signals that will swamp out what the chip itself can do.
Could you talk a little bit about the merging of wireless technology and cognitive communications?
Yes,
because the whole idea of big RF,
yeah,
so on comes into very.
that is what you'll hear tomorrow, and what we are announcing. That is what we're basically saying is that this era of learning, right, is upon us. The cognitive world, right, and the RF world is what we're very excited about. We have a couple of programs demonstrating sort of on a one-on-one, even adversarial world where I'm trying to do things that you don't want me to do. The cognition, that learning cycle has a lot of power. What we don't have is that on a large scale network to network. How do we have networks that actually start morphing what they're doing because of the presence of another network and actually scale that into a large city level demonstration? So that's really what the challenge we're focused on. Stay tuned, it goes live tomorrow. You'll hear a little bit more about it, but that's what we're excited about, right? Is not just dynamic spectrum access where you're hopping out of each other's way. We actually think the learning cycle that is. So just to take a step back from how we got here, in Las Vegas we have computers fighting hackers right in the Red Flag event in the Capture the Flag, which is usually the hacker community fighting each other's other hacking teams. We actually have a computer-on-computer demonstrator that you're automating the analysis of what's going wrong and how to fix it. And then we're actually going to enter that computer into a human competition. We'll probably lose, right? But we also lost to chess, and we also lost to Go, we also lost to, so there's a pathway there where you can actually imagine that a very different role of computers in terms of self-analysis. And we think that applies very much to the spectrum, and that's what the spectrum challenge is going to focus. Yeah.
Are you going to actively participate in the 5G global standards process that's starting up? Or?
We are not. We try to be out ahead. So a lot of what we're talking about we don't think is necessarily right. It may have intangible effects on that. We're also a technology demonstration organization. We don't set policy and we don't set standards. And so what we try to do is be as vocal as we can about our capabilities so that people that are actively in those debates know what the art of the possible is downstream. Yeah.
I've been trying to do it for the next 5 minutes. But anyway, a question. So I wanted to go a little bit, I think, the cognitive question a little bit higher level. And I wanted to go to the higher level. You said that, you know, we can avoid channels, but one of the factors of sharing a spectrum is time, right?
Mm-hmm.
And so even if the frequency is being used,
Yep.
as long as I characterize it holistically, I might be able to even communicate on the same channel.
Yep.
Because most of our communication is good.
Yeah, so I think what you're seeing here, right, is exactly that, right? That is, you know, frequency and moving out of the way of each other's frequency is one parameter of a huge search space, right? There's, you know, we're going to have many, many more directional beams. We're going to have polarization. We're going to have time, right? We've got waveform diversity, code diversity. Right? We have many, many tools to actually throw at this, right? Again, it's this complexity, man. How are you going to utilize those tools? And that's what we're going to ask the community to sort out in this sort of large-scale battle during the Grand Challenge.
So the question when you're trying to do that, how long in time would you take to converge to a good map that could be used by?
So this is long time scale mapping, right? I mean,
So that's a long. Okay.
yeah, this would be things that would be relevant from a human interface right now, right? So these are where transmitters exist in the world around you. Microsecond by microsecond, we're not sharing that information. We could, you know, actually I'm not sure we could from the speed of light in terms of exchanging all that information where it's being captured, but that's not really the focus of the program yet. But you could definitely imagine from the seconds timescales to more of the maybe milliseconds if you had the reason to. So this would give you sort of the time average power spectrum. So any one of these dots, right? This is power at one frequency, but if you click on that dot, it actually creates a power spectral density right across the spectrum that is synthesized from where the collectors were. But it's again, it's power spectral density. It's not. You could do what modern spectrum analyzers and whatnot are doing in terms of color coding that to kind of give you some level of information of burst patterns and whatnot.
Yeah, but the spectrum analyzer, you know, 10,000 plus in terms of cost. You need a cheap node to be able to do it.
So I think one thing I think, you know, that's absolutely true, but we have chip scale spectrum analyzers that we've developed. Right? So there's a lot that you can do, right? And what has happened, right? The phone went from yay big to yay big to yay big to a throwaway on the side of a digital processor, right? Unfortunately, as an RF guy. But that's a huge opportunity space. So what is the RF FPGA doing? It's using that scaling, right, into sub-chip scaling, right, and starting to build redundancy. The billions of transistors we have in a modern system allow you to do a huge amount of spectrum analysis. So we have, I think that right now, we have an A/D that's 64 gigabits per second, right, with a single chip. It's around a watt. So, you know, we're about to cross that threshold where you'll get spectrum analysis for basically free. So the question is, what do you do with it? Right? So,
Well, you can do a lot of.
you could, right? And presenting the user like, right, here's the spectrum running. You need a cycle to actually learn from it, and that's what we say that, you know, these type of technologies are going to exist specifically 5 years from now. I'm not worried about the hardware. I'm definitely worried about the management, you know, the intelligence in their system will know. Okay? And so spectrum analyzers are cheaper, right? But they're going to be, and I think radically cheaper in the future. In fact, spectrum analysis is going to be something that's just sort of an add-on to your system. University of Minnesota has created a 20 megahertz to 6 gig spectrum analyzer. It also labels the spectrum, kind of what I showed you earlier. And that would operate, it's a 45 nanometer CMOS device, and it would operate for 180 hours on a cell phone. So, you know, modern technology nodes, all right, they're great for the cloud. I think they're, you know, even better for mobile devices.
I don't know if you have time, but you had a slide where you had fiber optics, integrated optics, I didn't quite catch what was that an emitter? Were there
Yeah.
sensors? What's happening there?
So this is the LiDAR, right, with the rotating gimbal that's, you know, laser beam, it maps the world, they're amazing, they change the world. So this is the emitter, so this is the path, this is the fiber that gets distributed, these are the phase shifters. So just like we have RF phase shifters, we now have an optical phase shifter. We're actually steering light, right, without the rotating beam, and so the lasers are, you can actually start focusing, right, meaning there's something interesting there, let me scan, just like we do in the RF world, we can kind of point a beam. And so what's happening here, you know, and the other most important thing actually is hidden. This is an open loop first time demonstration. So in optics, it's a lot of hand tweaking, PhDs, and, you know, lab bench experiments, because of the quality of the tolerances you get when you have, you know, you're doing phase shifting at the optical frequencies. So this is an optical signal that comes in, gets split, goes through these phase shifters, then gets re-radiated out the front of that
So
chip.
it's synthetic aperture.
Yeah. This one is just projecting a specific image, right? I mean, each of these is a specific length to be able to create that image. There's also dynamic phase shifting versions of that. We have a new program called MOAB, which is a scalable LiDAR on a chip from things that will be commercially relevant to much larger sizes for military systems. And this is the type of technology that will be at the heart of that. What's that? Wrap up?
Yeah.
That's all good. So I'll be around for a bit, and Paul will be here tomorrow to kind of fill in the details of what I teased in order to start the challenge.
Great, thank you.